Okay, so we're going to work on 1.6. This is the last section in chapter 1, talking about logarithmic functions. Just like always, have a piece of paper ready, have your calculator, and we'll go through some stuff. You probably remember most of this, but if not, we'll go over them. Logarithmic functions are kind of like exponential functions, just in a different way. The exponential function and corresponding logarithmic function are inverses of each other. We begin by looking at the concept of inverse functions. Then we'll look at a logarithmic function. It's the inverse of exponential function. Logarithmic functions model and facilitate solving many types of problems, like Richter scale, decimal scale, and finding double and half-life exponential change. Okay? So let's first talk about a one-to-one function. A one-to-one function, every x has a unique y, and every y has a unique x. So here, f and g, each domain value corresponds to exactly one range value. Every x corresponds to an exactly one y. But the range value 2 corresponds to only the domain of value 4 in function f. So every x has to have a unique y, and every y has to have a unique x in order to be one-to-one. Here, this y has 2 values for x, so it's not one-to-one. Doesn't mean it's not a function, it just means it's not a one-to-one function. To be one-to-one, every x has to have a unique y, and every y has to have a unique x. So only function f is one-to-one. So a function f is said to be one-to-one if each range value corresponds to exactly one domain value. Okay? Any continuous function that is either increasing or decreasing for all domain values is one-to-one, as every x has a unique y, every y has a unique x. And for continuous function increases for some domain values and decreases for others, then it's not going to be one-to-one, just like the example we saw. Okay? We talked about that. Inverses of a function. If f is a one-to-one function, then the inverse of f is the function formed by interchanging the independent and dependent values for a function. So you remember where if you have y equals x plus 3, to do the inverse, you just mix the x and the y's, and that will be the inverse function. And what will result is if you had AB, then the inverse would be the point BA. If f is not one-to-one, then f does not have an inverse. Okay? So a logarithmic function, the exponential function y equals 2 raised to the x, increases for all its domain values to one-to-one. The inverse would be x equals 2 to the y. So again, y equals 2 raised to the x, we did that last time. To find the inverse, we reverse the x and the y's. That would be the inverse. And we call this inverse, bless you, logarithmic function with base 2, and write y equals log base 2x if and only if x equals 2 raised to y. Bottom line here, yes, they're inverses, but if you understand exponential, then you should be able to understand log. If I can get you to convert from one to the other, then hopefully they make sense. Once you understand one, you'll have a good appreciation for the other. Okay? So y equals log base 2 of x, and x equals 2 raised to the y are equivalent. Okay? So if I graph y equals 2 raised to the x, and then I graph y equals log base 2 of x, we're going to show that they're inverses. So there's the table of values showing that they're inverses. And then the graph also shows you that they're inverses because it's reflected over y equals x. This is all good to know. Setting us up to talk about logs. So the inverse of an exponential function is called a logarithmic function. B has to be greater than 0, b cannot be 1. Y equals log base b of x to logarithmic form is equivalent to x equals b raised to the y, the exponential form. The log of the base b of x is the exponent to which b must be raised to obtain x. The domain of logarithmic function is set of all positive real numbers. The range of logarithmic function sets all real numbers. Okay? So again, we can look at y equals b raised to the x. It's an inverse of y equals log base b of x. There's a relationship there. That's really what we're pointing out in all these slides, that there's a relationship. But here's what I want you to do. Okay? So to make sure we understand logs and exponents, if you can convert from one to the other, then you'll be okay. So on your paper, this is where I want you to write down, we're going to go from log to exponent, but they're the same. So I'll do the first one with you. Once you see the first one, then you're able to do the other two. Okay? So the first one is log base 5 of 125 equals 3. So here's the thinking. All those slides are setting up that if I have log base 5, 125 equals 3, I can convert that to an exponent. Here's what we do. The base is 5, so we write a large 5. What it equals is the exponent, which is 3. And then we're going to equal it to the center, which is 125. So 5 times 5 times 5 is 125, that's true. But here's what you need to understand. If you know that 5 to the third is 125, then you also know log base 5 of 125 is 3. They're the same. So our job is if you can go back and forth, you'll be able to understand each one. So right now, make sure you know which one goes where. Which one goes where. So I want you to try these two on your paper. So if you can go from logarithmic to exponential, then you can see the relationship between them. And if you understand exponents, you pretty much understand logs. And all those previous slides are setting this up. All those previous slides are setting it up. So for the first one, if I was going to go from logarithmic to exponential form, what would be the base? 4 raised to the 1/2 equals 2. They're exactly the same. They're the same. And just so to be clear, why is 4 to the 1/2 2? Not because half of 4 is 2. What's another way to write half? 0.5. What's another way? Square root. Because there's the 1, there's the 2. And what's the square root of 4? 2. So just to be careful, I don't want to do something that I'll make sure you understand. Okay? Let's do the next one. What would the base be? Raised to the equals. Perfect. Stop there. Now, does 3 to the negative 3 equal 127? Why? How do you change negative 3 to a positive 3? Move it to the denominator. And then what's 3 times 3 times 3? Now again, this stuff here, well, this one is this one, so let's make sure we're comfortable there. But 3 to the negative 3 equals 127. This is why we do appendix A. You should know to make a negative exponent positive is 1 over 3 to the third. 1 over 3 to the third is 1 over 27. That's why I have you do appendix A, because that's the stuff you should know. Are we comfortable going from log to exponent? Now we're going to go from exponent to log. So in your notes, there's all the answers, just like we just did. Now we're going to go the other way. Okay? So going to our paper, the first one is, if I have 3 to the negative 2 equals 1 over 9. Now, again, 3 to the negative 2 is 1 over 3 squared. 1 over 3 squared is 1 over 9. But if I'm going to convert that to log, this will be log. What's the base? What's the number on the inside? 1 over 9. And what does it equal? So that was a little weird, but it's the same thing. You can go from exponential to log, and from log to exponent. So when you're done, if you go back, 3 to the negative 2 equals 1 over 9. So I want you to be comfortable going from one to the other one. And then you get an appreciation that they're really the same stuff. Now we're going from exponential to log. And remember, all the slides are important, but the one that I stop and work on, that's the main stuff. A lot of it is set up and why, which is really important as well. All right. So if we have this, 125 raised to the 2/3 equals 25, this will be log, what's the base? 125, what's the number on the inside? And what does it equal? Oh, just 25. And it equals 2/3. So that's log, base 125, 25 would be in the inside, 2/3. Now, if you're wondering why does 125 to the 2/3 equal 25, that's the same as the cube root of 125 squared, which does equal 25. Okay? The next one, log, what would the base be? 2, what number's on the inside? And what does it equal? Okay? If we can go from exponential to log, and from log back, we realize it's the same stuff. We okay? Questions? Really, what number goes where? If I asked you to solve 2 equals log b of 100, what I want you to do is convert it to exponent and then find the number. So if I asked you to solve 2 equals log base b of 100, convert it to an exponent and then solve. Convert to an exponent and then solve. There's one little thing I need to point out. So first of all, if we convert, this will be written as what? B to the second power equals, and what number squared equals 100? Now I'm going to stop a second because some of you may have thought positive negative 10. It's a good idea, and yes, it could be positive negative 10, but because we're dealing with logs, remember that b has to be greater than or equal to 0. Because in logs, b has to be greater than or equal to 0. The only answer that works is 10. B has to be positive. It's a constraint of being a log. Okay, so since b is the base for a logarithm, it has to be a positive number. So b is 10 as the solution. Give this one a try. Solve log 6x, base 6x equals 5. Again, some of you are like, yeah, I remember this. We don't want to assume assume that all we've seen it or all we have not. So we go over it. Use your calculator to sit up and get a big number. Okay, this would be 6 raised to the 5th power equals x. What's 6 raised to the 5th power? That one. Now, there are a lot of rules here. And again, you have the slide. Don't worry about it. You can take a picture of it if you want. But you have all these rules. But I want to make sure they make sense. And these can come in handy when we deal with logs. Log base b of 1 is 0, because b to the 0 is always 1, no matter what that base is. Log base b of b is 1, because b to the 1 is always going to be b. So you can kind of figure them out as you look at it. Log base b of bx equals x, because b to the x equals b to the x. B raised to the log b of x equals x, as long as x is greater than 0. That's the left side. Basically, if you work them out, you'll figure them out automatically. On this side, this is just some special properties with logs. If I had log base b of m times n, I could rewrite that as log base b of m plus log base b of n. So when they're multiplied, you can separate it by addition and both have a log, same base. If we're dividing log base b of m over n, that's the same as log base b of m minus log b of n. And then log b raised to the mp, that p can move to the front. We can say p log b of m. And log b of m equals log b of n if and only if m equals n. So really we're going to talk about how to expand logs. When is that useful? Sometimes it makes life easier when we solve problems. This isn't really essential, but it's important stuff. And let me show you where it's going to be used. So if I had this expression, and I asked you to put it in a simpler form, okay? We're going to go through it together. Again, some of you may have done a lot with logs, some of you have not, so I don't want to assume anything. Okay? But what did we learn from the last example? We learned that if two things are being divided, I can separate it how? Subtraction. So this will be log b xy minus log b of tz. So since they're divided, I can separate it by subtraction, as long as they both get the log base expression. Are we okay? Now, when two things are being multiplied, they can be separated how? Addition. So log bx plus log by. Okay? Can I do that to the other side with t and z? But be careful, all this is being subtracted, so I would put it in parentheses to be safe. Log base b of t plus log b of z. I can distribute that subtraction. So I have log bx plus log by minus log bt minus log bz. Now, some of you are saying, you told me to simplify it. It looks a lot uglier now. It doesn't look simpler, it looks harder. That's just a matter of opinion. Depending on the problem, this may be useful. Again, it's not essential, essential super stuff, but it is important to know about logs and how we can move them around using log properties. That's why I'm kind of doing it with you. In case you haven't been exposed to it. Again, that's the work we just did. Okay, here's another one. Let's say we had log b xy raised to the 4th. And we want it in a similar form. Again, let's do it together just to kind of see how this rule will be used. Okay, when we have raised to the 4, if you remember back to those rules, where can the 4 go? in the front. Okay, stop there. Any questions? And then, when they're being multiplied, how can I separate it? Addition. But does the 4 go with the first, the second, or both? So it'd be 4 log bx plus 4 log by. And again, important, but I'm not spending forever on it. They're exactly the same. Sometimes these rules will come in handy when you want to solve with log or natural log, or if you want to simplify an expression. So it's good to know. Okay, a couple more. It's basically using the rules. Here's the next one. Here's the next one. 3 raised to x log 3b. Okay. We'll work it out together. So first of all, see this x in the front? Where can I put it? It's kind of the opposite of the last one. The x in the front could go as a exponent. So this would be log 3 raised to the log base 3b raised to the x. So again, the x in the front can move to the top. And then one of our properties says if we have 3 log base 3 of bx, this base and this base will leave us just with bx. It's another one of those properties on the left side. That's it. We could also go the opposite way. So in this example, it's already expanded. We can condense it. So how can these properties be used? Well, here's the problem, first of all. And what am I pointing out? Log base 4, log base 4. Do they match? Because they match, I can put them together. When they're being added, how can I put them together? These two will be multiplied. Okay? Now, the problem with solving these is we don't really know our logs very well or where the keys are and all the options we have. So let's convert this to an exponent. If I convert this to an exponent, this will be what? 4 to the third equals x plus 6, x minus 6. So again, trying to solve a log problem, let's get there. Now, if I clean this up, which all of us are good at, x times x is x squared minus 6x plus 6x minus 36. 4 to the third is 64. Then, if I subtract 64, x squared minus 100 equals 0. Add 100, x squared equals 100. Therefore, x equals plus or minus 10. But we need to be careful with logs. When we deal with logs, we have to know there's certain things logs can be and certain things logs cannot be. So when we go in and we realize that the negative one is not a solution. When you go in and check, the negative one doesn't work. The only one that works is going to be 10. The only thing I'm going to be careful about saying that is that when you plug it in, if it ends up becoming negative, it ends up being a problem, then it's a problem. But it's not that negative cannot work. If I take negative, plug it in, it ends up being positive, then it's okay. So think of it as that when you're done, plug it in, because logs have certain rules. So if I took in 10, plug it into the original, it will work. But if I took in negative 10, plugged it in, it will not work, because log has a constraint. That's my only little disclaimer. And again, some of you guys know all this, some of you guys this is new. Some teachers in college algebra really stress logs, some teachers breeze over. Okay? So not to stress you out, just some log properties. Now, of all possible logarithmic bases, e and 10 are used most often. Common logs are with base 10. In mathematics notation, log x means log base 10. So if you see log of x, it's understood that the base is 10. And natural logs are logarithms with base e. So if you had log e of x, that's the same thing as ln of x. So if you go to your calculator, you're going to find all these buttons. So on the left side of your calculator, you have log, you have ln. Log, ln. If you use that log button, it's assumed to be log base 10. So this example says, give the exact solution in terms of e. I'm not going to stress too much about this one, but the exact solution in terms of e. Let's do this one together. So if I had ln of x plus 1 minus ln of x equals 1. Let's use our properties. And again, still logs. What does minus mean? Divide. So this will be ln of x plus 1 over x equals 1. You may remember back, again, not essential, but you may remember back that ln x plus 1 over x is really e. Look at the 1. And I'm not really going to do much more with this one. I just wanted to show that the conversion, and then, again, not essential, but this is where the e comes from. So I'm going to stop there on that one. I'll show you the answer on it, but I don't want to get too much into the e's and all that. Okay? As previously noted in the calculator, you have the log and the natural log. Now we're going to use our calculator to answer a few questions. Okay? So go to your calculator, put in log of 5,287, see if you get that answer. Put in natural log of 0.0000124, see if you get that answer. And then type in log of negative 2.88, see what happens there. So becoming familiar with the buttons in the calculator. Okay, so in the calculator, let's do that first one. If I do log of 5,287. That will give you 3.7232093. Keeps on going and going and going. If I did natural log of 0.1234124, that would give you negative 11.2978. Keep going. But then, what's interesting about the last one, type in log of negative 2.88, and your calculator explodes. No, that's not true. But it says no real answer. What does that mean? Why? Well, again, let's put an x here, and if there's no base, what's the base assumed to be? 10. So if I convert that to an exponent, 10 to the what would give you a negative 2.88. Is there any number that if I 10 raised to the 1, 10 raised to 2, even 10 raised to the negative, you'll never get a negative answer? So here, there's no real solution. Remember, there's some constraints on logs. Just won't work. We're just focusing on the one. So in a calculator, that's what happens when you plug it in. Again, no real answer, even an error. And that's the one. Okay? So let's say I wanted you to solve log x equals negative 1.864. Question? We'll talk about that in a little bit. Well, actually, let's take care of that now. His question was, what if I had a different base, like log base 3 of 5? Okay, let's take care of that now. Depending on your calculator, if your calculator, if you want to practice, go to the math button, and go down to A. Not all calculators will have it, but yours may. If you have math down to A and you choose log base, it will allow you to put a base of 3 and a base of 5, or a number of 5 inside, and you can figure that out and get 1.46497. Now, if you don't have it, it's really not a big deal, because there's a change of base formula. So if you don't have that in the calculator, this can also be written as log 5 over log of 3. It's just another way to write it. And if you put log of 5 divided by log of 3, you get the same answer. So how do you do other bases than 10? That's how. Did your calculator have the math one? Then you'll do the change of base. And it means the same. Good? So let's get back to this problem. If I had log of x equals negative 1.864, and I want to solve for x, what's the base? 10. Change it to an exponent and use your calculator. Change it to an exponent and use the calculator. See if you can find where the key is in the calculator. So first, change it to an exponent, and then use your calculator. And then we'll even check it with calculator. But all these things are coming up, and I'm just pointing them out. Okay? So if I was going to change this to an exponent, what would it be? Good. That would be my answer. Now, you could just type 10 raised to, but I do want to point out that you also have a 10 raised to button. So if you hit second log, you get a 10 raised to negative 1.864, and you get x equals 0.0136773. Keeps going. So you do have that button in your calculator. And I want to practice the buttons. So when I'm done, if I take that answer and plug it back in, what should it equal? Negative 1.864, right? Let's see if it does. Log. I'm just going to hit second negative for answer, and it comes back. Second negative gives you the previous answer. Second negative gives you the previous answer. So all these can be checked. And again, notice I'm going a little fast through them. I'm just kind of hitting the ones that I want to make sure you're aware of. So if I ask you to solve ln of x equals 3.416. Some of you may have done it, some of you may have not. Solve ln of x equals 3.416. You may or may not remember, if I want to get x by itself, how do I get rid of ln? What's the opposite of ln? Anybody remember from algebra? Opposite of ln? We know the opposite of plus is minus, opposite of multiply is divide. The opposite of ln is e. E. If you e in ln, we're left with x equals e to the 3.416. Practice where that button is. We did e last class. So practice where that button is. So the opposite of ln is e. Opposite of ln is e. Now practice that button from last time. E second ln 3.416 gives you 30.447. And again, plug it back into the original and you get it back. In the calculator, that's what it looks like. Okay, what if I had, and again, if you remember these, great. If not, things to remember. What if I asked you to solve 10 raised to the x equals 15? Ten raised to the x equals 15. Okay, so the problem is 10 raised to the x. What can we do? Well, if I want that x to be moved out, what I could do is log both sides. Now, why does that work? If I have log of 10 raised to the x equals log of 15, how does this come in to be useful? If I log both sides, remember my log properties? What happens to the x? It can be moved to the front. Now, I will point out a couple ways to do it. What's the base here? If there's no base, what's the base? And what's log base 10 of 10? When the two numbers match, what does that whole thing become? So what does that become if I did the log of 10? If the base is 10, if the base is 10 and the number's 10, what do you think I end up with? 1, because 10 to the 1 equals 10, right? So that's one of those properties too. But even if you didn't notice that, divide by log base 10, divide by log base 10, x equals log of 15 divided by log of 10. Plug that into the calculator. Practice the button. we already know log base 10 is 1. But if you went through it, the practice typing, you will get 1.1761. Get all these things come up from all these different log properties that are helpful in solving problems. Again, it's the same thing as log that you divide by. Good. And sometimes you'll notice the slides skip a little bit. Like, where did that come from? You can see where it came from. You will. Sure. Okay, one more problem to solve. What if you had 5 raised to the x equals 11, and you're trying to solve for x? Okay, now we could have done the same thing we did last time with the logs, but let me show you a different way. Log and natural log have the same properties. So again, the problem is the x is up here. The problem is the x is up here. If I ln both sides, that's natural log. If I ln both sides, that's natural log, and it has the same properties. So if I natural log both sides, where will the x go now, going by the properties? To the front. And then, to solve for x, how do I get rid of times ln of 5? Divide by ln of 5, divide by ln of 5. So x equals ln 11 divided by ln of 5. Practice those buttons. Yep.
How do you know what's
Doesn't matter. Either one works. Both ways, same answer. This just gives us an opportunity to try both. But they both have the same log properties. They're both the same. They both do the same things. If you do it the other way or this way, you'll get the same answer. Okay, remember what his question was. What if I did log instead of ln? What would happen? Well, if you do natural log of ln of 11 divided by ln of 5, there you get 1.489896. If you did log of 11 divided by log of 5, you get the same answer. It's kind of like you have a bunch of ways of doing the same thing. Okay? So suppose you had y equals log base b of x for some suitable base b. B to the y equals x, log of by equals log of x, y log b equals log of x, y equals log x of log b. Since y equals log b of x, suitable to find log b, x equals log b over log x over log b. All this is just going to help you understand the change of base formula, basically how to manipulate it around. So basically, what is this saying? Just to give you a quick idea. Remember, we just did, if I had log base 3 of x, if you could do that in the calculator, great. If you can't, that could be written as log 5 over log of 3, and you can get the answer that way. Remember doing that? This whole slide says the same thing. Log of x over log of 8, same thing. Just sometimes they write it in symbols, so we don't have the full meaning. So different investments can be compared by using doubling times. The doubling time of exponential growth is the length of time it takes the value to double. An investment with a shorter doubling time has a higher rate of return. Logarithms provide a convenient tool for solving double problems. Okay? So how long to the next whole year will it take money to double if it's invested at 15% compounded annually? So if you're compounded annually, we use the formula A equals P times 1 plus R over M, M to the T. So formula given, R is 0.15, M is 1, A equals 2P. That means when does the account double? So if I plug into the equation, we get 2P equals P times 1 plus 0.15T. Okay? So let me explain all this. Okay? So when will P double? So A becomes 2P, the double of P. 1 plus R is 0.15. M is yearly, so M is 1. That's 1. So we're just left with T. So bottom line is, how do I solve this? Bottom line is, how do you solve this? Okay? Well, step 1, you may notice that there's a P here and a P here. So if I divide by P and divide by P, I'm left with 2 equals 1 plus 0.15T. And you may also notice that 1 plus 0.15 would be 1.15T. Okay? So we just did this a little bit ago. So solve for T. Solve for T. And you have a couple different ways of doing it. Solve for T. This is just an application of that. And round to the mirror sheet. I'm going to work it out as you're working it out. I'm going to ln both sides. Which means ln of 2, the t can go in front. ln of 1.15. Divide by ln of 1.15. Divide by ln of 1.15. T equals ln of 2 divided by ln of 1.15. And again, if you did log, same thing. If you did log, same thing. That gives you, if you put that in the calculator, about 4.9595, which is about 5 years. How long will it take to double? 5 years. Now, if you did log of 2 over log of 1.15, same thing. Same thing, same thing. We okay? Question? This one said round to the whole year. On my lab, they're very specific, 4 decimal places, 3 decimal places. For me, whatever's appropriate. So on a hand paper test, 3, 4, whatever the number means. But if it's 0.000005, you can't go 3 or 4, depends on the number. I'm not as picky as the other question? Oh.
Divided by ln by 2 by both sides. You
figured it out? Okay. All right, so to end this section, we're like, yeah, it's almost over. We did linear regression, we did quadratic regression, we did cubic regression, we did exponential regression. Now we're going to do logarithmic regression. Okay? So logarithmic regression has a specific shape. And if your regression looks like that, then logarithmic is appropriate. So before we do anything, I'm going to use this as a nice reminder of all the regressions. Okay? So a cordless screwdriver is sold through a national chain of discount stores. A marketing company established the following price demand table, where X is the number of screwdrivers people are willing to buy at each month at a price P dollars. So 1,000 screwdrivers, price 91. 2,000 screwdrivers if the price was 73. Notice the cheaper the price, the more people want it. Are we okay? Here's what I want you to do, and this is going to be basically our review of all the regressions. So I'm going to take my time on this, and the reason why I'm taking my time on this is that we're actually reviewing all of our regressions and reviewing everything we did with the calculator. So I'm going to put my data down, and I'm going to ask you to do certain things that we've already done in every regression, but we're going to do them one at a time. Okay? And this is kind of the steps I want you to do for every regression. Linear, quadratic, exponential, cubic, and now logarithmic. Okay? So step one, don't touch your calculator. Okay? The first thing I want you to do is I want you to sketch the window for this data. So what goes on the x-axis, what goes on the y-axis, what would you start with, what would you end with? Just do that first. Don't touch your calculator. Don't mess with your calculator. Understand the problem first. That's step one. Okay? So on my x-axis is number of screwdrivers. It goes from 1,000 to 5,000. What would you start with? I'd probably start with 0. If you start with 1,000, that's fine, but I'd start with 0 too. And what would you end with? 6,000, and what would you count by? Perfect. So 0, 1,000, 2,000, 3,000, 4,000, 5,000, ending with 6,000. Okay? And then on my y-axis is price of demand. And the lowest is 53 and the highest is 91. So what would you start with? 50? Okay? So right in the corner, 50. And what would you end with? And what would you count by? Probably 10. So 50, 60, 70, 80, 90, 100. We okay? And put the dots. Do it by hand. So 1,000, 91, 2,000, 73, 3,000, 64, 4,000, 56, 5,000, 53. Now, notice that curve downward. Okay, it's not a line. Kind of looks quadratic, but quadratic would be a U shape. That's kind of flattening out. It's not exponential, which starts out low, shoots up high. It kind of looks a little exponential, but it has that downward curve. So we're going to go with logarithmic. Okay, but before we do any regressions, does everybody have the graph on their paper? Now get the graph on your calculator. We're going to put X in list 5. We're going to put Y in list 6. So we're going to use all of our lists. And in your calculator, I want those dots. Just like we did for linear, quadratic, cubic, exponential, now we're going to do it for logarithmic. And my only little advice is, the very first thing you should do, go to Y equals, make sure all your plots are off to start with, and make sure there's nothing in Y1, nothing in Y2. So always go to Y1, Y equals, Make sure you have a clean calculator. Then stat, edit. We're using list 5 and 6 to put our data. I like you to use a different list. If you always use 1 and 2, my only concern is you don't know how to do any other list. So let's just try 5 and 6 if you could. If you want to do 1 and 2, you can do whatever you want. But I just want us to be comfortable using any list. But get the dots, and if you're very fast, get the dots and the line that goes through it using logarithmic regression. And if you are fast, you're not going to find log. You're not going to find log in the regressions. You're going to find natural log, ln. So it's actually ln regression. ln, which is natural log. Take some time, really make sure this makes sense for you. Whenever you do ln regression. And then I'm going to ask you a couple questions. But if you can do this regression, you can do them all. And if you need help, raise your hand. But when you're done, you have the dots and the line that goes through it, and then we can answer some questions. You can do linear, you can do quadratic, you can do cubic, you can do exponential, and you can do logarithmic. So logarithmic regression or ln regression, do natural log regression and make the line go through it. So when you're done, you should have the dots and the line that goes through the question. You should have the dots and the line. That's just if you want to automatically. But I have to teach it with color. I like it with like
Oh, I know.
Okay, so let's make sure that everyone has the dots in their calculator first. Okay? So, how do I put the data in the calculator? You push stat, number 1 for edit, and I put x's in list 5, y in list 6. If one number is wrong, it throws it off. Then I go to second y equals. I go into plot 1, turn it on, choose scatter plot. X is list 5, second 5. Y is list 6, second 6. Stop there. Now you could hit zoom 9. Zoom 9 does the window for you, but I don't want to use zoom 9. I want to make my own window. So first of all, did everybody put the data in list 5 and list 6? And did everybody turn their plot on? Choose scatter plot 5 and 6. Everybody good so far? Hit window, window. What is our x minimum? X maximum? X scale? Y minimum? 50, Y max? 100, and Y scale? Hit graph. There's your dots. Anybody need help with that? It's the same for linear, quadratic, cubic, exponential. Question? If you didn't get it, raise your hand. I'll come over and check. So there we got the dots, 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 dots. Now, the new regression is called logarithmic. But if I hit stat, calculate, where all the regressions are, you will not see logarithmic. But I will warn you, you will see something called logistic. That's different. That's something else. We're looking for ln. So anytime I ask for logarithmic, we're going to use ln. Why ln? ln is natural log. So we choose 9. We tell it second 5, second 6. If your calculator doesn't ask for x and y, it just blinks. You have to do list 5, comma, list 6. Go down to calculate. Everybody should see this. Same number, same everything. Okay? The r squared in the r is just telling us if it's a good fit or not. If it's close to 1, is it a good fit? Is this a good fit?
Yeah.
Really good fit. Okay? You're going to put a in for a, b in for b. How many decimal places? 3 or 4. If you do the homework, it's going to ask you for, it's going to tell you how many. But I'm going to put, let's say, d of x, doesn't matter which we use it, a and d of x. So I'll put 256.47 plus negative 24.04 ln of x. You could also write a d of x equals 256.47 minus 24.04 ln of x. Either one's fine. But to make sure it's correct, I'm going to go to y equals, I'm going to type it in, 256.47 minus 24.04 ln, we know what that button is, x, hit graph, and the line should go right through the dots. We okay? Now, I'm going to come around if anybody needs help, but here are the 2 questions that I can ask you with this problem. Question 1. How many, actually no. Question 1. What price for, let's say, 3,500 screwdrivers? Question 1. What price would you have to charge for 3,500 screwdrivers? And question 2. How many screwdrivers at price $60? However you want to do it. You can do it using a graph, you can do it using algebra, but answer those 2 questions. What price would you have to set it for 3,500 screwdrivers? And how many screwdrivers at the price of $60? Good work. You do it a couple different ways. There are 2 questions you can answer with any regression. Same line. If you have questions, if your picture is weird, let me know. I can help you. I didn't mean for them to be close. It wasn't on purpose. again, I can ask you the same questions for linear, quadratic, exponential, logarithmic, cubic, always ask the same one. You could do it algebraically, you could do it graphically, you could do it totally in the calculator, there are a lot of different ways. Yeah. You get traits every time you math. So, what are you trying to do? They're close. I didn't mean for them to be close. I'm happy with that, but that's not my intention. All right, so here's the deal. The point of this is, does 3,500 go in for X or does it go in for Y? It goes in for X. So this would be D of 3,500 equals 256.47 minus 2404 ln of 3,500. So to do this, look how many ways I taught you. You could, number one, just type it in. You could easily say 256.47 minus 24.04 ln of 3,500. You can type that in, and you get an answer of what? $60.29. That's one way. Some of you also remember the table feature? If I hit second graph, and you set up your table like we did last time, X is 3,500, you can get the answer that way. Okay? A third way, which I haven't taught you, but some of you may remember from another class, if you hit graph, hit second trace, number 1 for value. What value would you like to see? 3,500. This is optional. And it shows you where it is on the graph. So 3 ways of doing the same thing. Now, the second question, which we did go over this type, does 60 go in for X or does it go in for Y? It goes in for Y. So the 2 ways you can do this equals 60 is you can either do the algebra or you could use the calculator. So let's do algebra first. If I wanted to solve this, I would subtract 256.47, subtract 256.47, which gives me negative 2404 ln of x equals negative 196.47. Divide by negative 2404. Divide by negative 2404. ln of x equals 8.1726. And then we learned today, or maybe before, how do you get rid of ln? E both sides. So the E of that answer gives you 3,542.645. Or just 3,540. So I could have done algebra, but as I walked around, I didn't see anybody that did algebra, but you could have. Did anybody figure out the calculator way that we did in the past? When y is 60? When y is 60? When y is 60? You're saying that a lot. When y is 60, go to your calculator, make y 60. Isn't y 60? Hit graph. Where's the answer? Where they find it. Find where they intersect. Go to your calculator, make y 60. See if you remember, because we did intersect a lot. to review. What do I push to find where they intersect? What do you push? Second trace, 5, enter, enter, enter. Same answer. Good?